Hi guys, Mrs. Delisin here. Welcome to another lesson of AP Statistics. Today's lesson is estimating a proportion. When you toss a Hershey Kiss, it sometimes lands flat and sometimes lands on its side. What proportion of tosses will land flat? Each group of 4 selects a random sample of 50 Hershey's Kisses to bring back to their desk, toss the 50 kisses, and calculate the proportion that will land flat. So I also did mine, and I'm going to be using the one I have, which is I tossed 50 kisses, and I got 21 of them landed flat, and that is 0.42. So 42% of the kisses that I have in the sample of 50 landed flat. It might be yours if you have to do it on your own. It might be higher than 0.42. It might be lower than 0.42, or it might be 0.42. We don't know, right? The idea is what I have right now is a sample. Okay, we have now identifying our population, sample, parameter, and statistic. So my parameter is all Hershey's Kisses. My sample would be the 50, can I put HK, right? Hershey's Kisses. My statistic is the one that I have, which is 0.42. My parameter, I don't know what it is because I don't have the whole entire Kisses or the population of Hershey's Kisses, right? What I can do though is estimate that. So what I'm trying to do is to estimate the true proportion that will land flat. Okay, and again, I don't know that, but I am trying to describe it, but my parameter would have been the true proportion of Hershey's Kisses that will land flat. Was the sample a random sample, and why it is important, or why is this important? Let's read back. Each group of 4 selects a random sample of 50. So yes, it is a random sample. And if you remember chapter 4, we had this experiment, or we had this sample where we did, is this random sample or is this a random assignment, right? And we studied why it was important for it to be a random sample. And hopefully you remember that why it's important for a sample to be random. Oh yes, he or she, whatever, it was a random sample, randomly sampled 50 Hershey's Kisses. So we can generalize to the population of kisses. Right? So it's important that we do a random sample so that we can generalize our result to the whole population. And this is our first condition. Condition number 1. We have to make sure that it is a random sample of Hershey's Kisses, a random sample of students. It has to be a random sample. Moving on. What is the formula for calculating the standard deviation of the sampling distribution of p-hat? We know that the formula of the standard deviation of the sampling distribution is the square root of p, 1 minus p over n. What condition must be met to use this formula? Has it been met? So we already know that in order for us to use this formula, we need to make sure that we pass the 10% condition. So let's see if it passes. Our number of sample is 50. 50 is definitely less than a tenth or less than 10% of all Hershey's Kisses. Right? So 10% condition is met. 10% condition is met. And this is our condition number 2. We need to make sure, condition number 1, that it was a random sample. We need to make sure that it passes 10% condition. That is our condition number 2. Okay, moving on. We don't know, you know how we have our formula P1 minus P over N? We don't know the value of P. That's the whole point of a confidence interval, right? We don't know the true proportion. That's why we're using our sample proportion to estimate the true proportion. So we will use P hat instead. So we are going to calculate the standard deviation as if we are using a P hat instead of a P. So our formula would be using the P hat 1 minus P hat over N. Again, I'm using P hat, not P, because I don't have the P. What I do have is the sample proportion. And this is 0.42 times 1 minus 0.42 is 0.58 over, of course, 50. That is 0.0698. So this is my standard deviation. But because we used our P hat, not a P, we call this one a standard error. Standard, where do I put that there? Standard error of P hat. And the formula will now change into standard error of P hat equals the square root of P hat 1 minus P hat over N. Okay, so we'll put that formula here in red. P hat equals P hat 1 minus P hat over N. And remember now, we call this standard error. Standard error because I know it's a standard deviation, but why do we call it standard error? We call it that because we're not using the P inside the radical, we're using the P hat. Okay, would it be appropriate to use normal distribution to model the sampling distribution of P hat? Justify your answer. In order for us to do that, we have to check large count. And again, large count condition. And again, we don't have the P, so we are going to be using N times P hat and N 1 minus P hat. And N is 50 times 0.42 is 21. And then we have 50 times times 0.58, that is equal to 29. Both of these are greater than or equal to 10. So yes, it is approximately normal. Remember now, never say it is normal. Always add the word approximately. And this is the next condition that we have to check. Okay, let's recap. Condition number 1, we have to make sure if it's random. Condition number 2, we have to check 10% condition. Condition number 3, we need to make sure that it is approximately normal. So we have 3 conditions so far. Moving on. In a normal distribution, 95% of the data lies within, do you guys remember this? There. Do you guys remember 68% lies within 1 standard deviation of the mean, from the mean? And then we have 95% lies 2 standard deviations above and below the mean. And then we have 99.7 lies within 3 standard deviations below and above the mean. So that is what we call the empirical rule. So what we know is, using the table, approximately it's about 2 standard deviations of the mean. This value is what we call the critical value. And critical value is represented with letter Z. Critical value is represented with a Z and a star on the top. Because Z is used for Z-score, right? So Z with a star is called the critical value. What is a critical value? Okay, 80% of the data lies within the standard deviation of the mean. So let me draw that for you over here. So if I know that this is 68%, I know this is 90%, right? So 80% lies within this. So when it's asking you within what's the z-score for these two? Okay, of course, we can calculate that using our calculator. I will show you that also. But for now, I'm going to use the table to determine 80%, like the critical value. And you will find that on your tables and formula and worksheet. And you'll go, see how this is the z-score, table A. You go all the way down. And at the bottom, or I passed it there. All the way at the bottom, you will see it's called confidence level. Okay, and then we will look for 80%. Right here is 80%. The number right on the top of 80% is 1.282. That is the critical value of 80%. Okay, so I'm going to go ahead 1.282. And then I'll go back to 90%. 90% of the data lies within 90%. There you go, 1.645. And I'm also going to just do 95%. It's 1.96. Okay, we know that 95% is within 2 standard deviations above and below the mean. But the 2 is actually... what's that called? The 2 is actually an estimate. The true number really is 1.96. Okay, so let's go back to our picture here. 90% would be 1.645. 95% is 1.960. So when I say about 2 standard deviation, I really meant 1.96. Does that make sense? 99%, I should have just also... 99% all the way here, a number on top is 2.576. So that is 2.576. I would also like you to do it in the calculator. If you want to do it in the calculator, not the table, okay? Because what if we're given a number, we're given a confidence level that is not in the calculator. It's not in the table. This is what you're going to do. When I say 80%, this whole entire thing is 80%. Let me put that thing. This is 80% of the distribution, right? This one right here. So we have 10% here, and we have 10% there, right? To make 100%, obviously, correct? And so what I'm going to do is I'm going to do inverse normal. Inverse normal is when we have the area and we want the z-score, remember? But in the inverse normal, you are going to put inverse normal, and you are going to put the tail percentage. So when I say tail percentage, I am putting either this 10% or that 10%, it doesn't matter. So if you go to inverse normal, hopefully you are going to do that in the calculator. Inverse normal, and you put 0.10 in it. Don't change the mean, don't change the standard deviation, keep it as 0 and 1. You should get 1.282. Okay? So if I want to get the critical value of the 90% using a calculator, I would have to go, let me erase this. I would have to go 90%. 90% is here. So I have left over 5% in there, 5% in there. Does that make sense? So in the inverse normal, I am inverse normal. I am going to put 0.05 in the area to get 1.645. Okay? I hope that is making sense. Moving on. And of course, you can always use the table. Calculate the margin of error for a 95% interval by multiplying the critical value and the standard deviation you found above. So margin of error, I'm going to call it ME. Margin of error is the critical value. Remember, critical value is a Z star times the standard deviation. Standard deviation is SE of P hat, right? So my Z for 95% is 1.96. Multiply that with my standard deviation. Let me go up a little bit. I got right over here 0.0698. So I'm going to multiply that 0.0698. I will get 0.137. And this is what you call your margin of error. So now we know that the formula for margin of error is just getting the z-score and multiplying it with the standard error or multiplying it with the standard deviation. Hopefully that is making sense. Find the 95% confidence interval using point estimate plus and minus margin of error. Okay, I know that my margin of error plus and minus, I know my margin of error is 0.37. Okay, and then my point estimate is my sample proportion. Let's go back. My sample proportion that I got is 21 out of 50, which is 42%, 0.42. So I am now going to make my interval by using the sample that I have. So lower number first, 0.42 minus 0.137 is 0.283. Comma, 0.42 plus 0.137 is 0.557. This is now what we call our confidence interval. Okay, then let's recap with the formula of that one. That was a P hat plus and minus. The formula of the Z of my margin of error was a Z star. P hat 1 minus P hat over N. So this is now our new formula, which is unfortunately not given on the AP exam. But of course, you can just like combine those, right? Combine the standard deviation and the P hat. Okay, I am going to skip number 11 and number 12. I am going to do the important idea section right away. What did we learn? We learned to check 3 different conditions, right? We learned to check conditions. The first condition is it a random sample? Right? Second condition is did it pass the 10% condition? And then large count condition, is it normal? Okay? And then we're going to our critical value. Just example, 90% has a Z star of 90% has a Z star of 1.645. 95% has a Z star of 1.960. These are the common ones. 99% has a Z star of 2.576. Of course, you do not have to memorize that because you have the calculator and you have the table. But if you want to find the calculator, the Z star in the calculator, we are going to do inverse normal. And then in the inverse normal, you're going to put the tail percentage. Right? So if you are trying to get the 80%, so the tail of 80% would be 20 divided by 2. And then if you're going to get the 90%, the tail would be 10, 5 on both sides. So you're going to have 0.05 in the inverse normal. Okay, moving on. Our formula for confidence interval for P is point of estimate plus and minus Z star and P hat 1 minus P hat over N. And remember, this is called the standard error. Okay. What do you want to be when you grow up? I knew what I wanted to be when I grew up and when I was when I was in kindergarten. So hopefully by now you guys know what you're going to do when you grow up. According to a nationwide survey of a random sample of 1,000 kids, I have my N in there. My N is 1,000. Under the age of 12, some kids want to be a ninja, a dragon keeper, dancing unicorn, and even an octopus. 55 of the 1,000 kids, so 55 out of 1,000, want to be a doctor. But everybody wants to be a doctor when they're a kid, right? We would like to use this study to find a 98% confidence interval for the true proportion of kids who want to be a doctor. Identify the parameter of interest. Parameter means what are we trying to get? We want to get the true proportion, of kids who want to be a doctor. Okay, next, check the conditions for constructing a confidence interval for P and make sure they are all met. First, we're going to start with our first condition, which is random. Let's put 1 in it. Was it random? A random sample of 1,000 kids. So we're good. Next, we have, why do we check if it's a random sample? We check if it's a random sample so we can generalize the result to the population. Next condition, 10% condition. We have here 1,000 is definitely less than 10% of all kids nationwide. Because it did say according to a nationwide survey. Last condition is the large count condition. Let's just put LC. The 1,000 times, let's put our P hat here first. Our P hat is equal to 55 out of 1,000. That's what's that? 0.55. Okay. So, there you go. This is 0.055. And then 1,000 times 1 minus 0.055 is 0.945. Okay, both of them, this is equal to 55, I'm pretty sure. And then this is, of course, 945. And both of them are greater than, I don't have to say equal, but just a habit, I always just put it, that 945 and 55 are both greater than 10. So this is approximately normal. Approximately normal. There you go. Find the critical value for a 98% confidence interval, then calculate the interval. So critical value for 98, we don't have that do we have that over there on the top? We don't. So what we're going to do is we're going to do our table and we do 98%, that is 0.326. Okay, 0.326. I think I can round that to 2.33. Okay, so let's round that. For 98%, the Z star for that is 2.33, rounded, okay? And I got that from the table. Now, let's calculate our interval. And we are going to do point estimate. Let's put that there. Point estimate plus and minus the margin of error. And we know that the point estimate is just the p hat plus and minus the z star. And then we have our p hat, 1 minus p hat over n. So let's plug in. Our p hat was 0.055, right? 55 out of 1,000. And then our z star is 0.33. And then I have 0.0551 minus, I can just put 1 minus 0.00055 is 0.945 over how many people are in the sample. Okay, so technically what you could do in the calculator, because you cannot put the whole entire plus and minus, right? So I suggest that you solve this part first. Okay, so let us solve that. Hold on. I haven't prepared solving. I do have the answer though, right? So the answer here would be 0.038, comma 0.72. All right, because there's a way to just plug all of this in the calculator, but I am going to teach you that after. So let us solve this one first, 0.55 plus and minus. So we are going to type 2.33. We have 0.055 times 0.945 over 1,000. And we are going to get 0.01678 there. Okay? And you're just going to go 0.055 plus 0.0168 and then 0.055 minus 0.0168. And then, of course, we have to interpret our interval in context. Let's do that. We are 98% confident that the interval from 0.038 to 0.072 captures the true proportion of kids who want to be a doctor. There you go. Okay? There you have it. So every time you are solving for confidence interval, do not forget to check for 3 different kinds of condition. First condition, you need to make sure that it was a random sample. And why do we need to check if it was a random sample? We need to check if it was a random sample so that we can generalize the result to the whole population. Now, why do we need to check if it was passing 10% condition? Because we need to make sure if it's independent. And then the last one, we have to check our large count condition. And we check large count condition because we want to make sure that it's approximately normal. All right, there you have it. I hope that this whole entire lesson will help you understand how to create confidence interval for any context. Thank you guys. If you have any questions, please let me know. I'll see you guys on the next